Hi, this is Jordan Stevens and Danica Dvorak with Engineering 460 Presentation 8. Unfortunately, Danica and I could not meet this week and go through this together, but she'll be doing our homework and I'll be doing our Presentation 8. So moving on, our first section is our GG1 simulation. This denotes a queuing system. The first G is the arrival distribution, the second G is the service distribution, and the final one is the amount of servers that they're going to be going through. The G's typically are representative of a general distribution, and the aim of a GG1 is to find the average queue length in the system. We're going to be, and for the simulation in the book, we're going to be using simulation to predict the GG1 values. So now we're going to be going into state changes. Since this is a discrete event simulation, there are going to be state changes that are discrete points in the time where an action happens. So in this system, there are three phases. You could call it a three-phase system. There is a bound state, which is the customer entering the system, another bound state, the customer leaving the system, and a conditional state, which is the customer being served, what things happen during that customer being served. Okay, so the customer entering the system and leaving systems are based on different distribution streams. This allows for, we don't want our them to be together because there could be this leads to high correlation in the simulation method. Also, it just doesn't make sense that your arrival distribution and your departure distribution, which are the two distributions we're going to be using, are the same distribution, are retrieved from the same distribution. And lastly, there is a regenerative cycle. Whenever the system's empty, it basically resets so that we don't have too much correlation. This allows that whenever the system is empty and the line is empty, so basically there's nothing happening in the system, it basically just refreshes the random seed for both of the distributions and resets all of the values. So moving into this, we'll just go into the algorithm they have in the book. The T is the partial length of current cycle. So basically, this is basically where we're going to be figuring out whether it is an arrival distribution or a departure distribution. We can see that by this T equals min of TA and TD. We can see that T is time of next arrival and TD is time of next departure. So we're taking the min of this to figure out if there's an arrival coming into the system or if there's a entity is departing the system. So based on this, we also have the T-prev. This is the state in the previous system, so this is the state previously shown. The L, which is the number of customers in the system, so the L variable is really what we're looking at. We're trying to look at the average amount of customers in the system. The A is the arrival time, and the D is the service duration, so that's kind of like the departure time. It's how much time does the customer take at the server until it departs. Finally, we have the R, that is the time from 0 to T of the, so we're trying to find the expected value of the line from 0 to that T. And D is the time since the last event. Okay, so as we go through the algorithm, we basically initialize, figuring out if we have an arrival coming in the system or a departure coming from the system. From this, we have our if conditions. These if conditions basically figure out what state we're in. So, if we have our time is an arrival coming in and our line is equal to system, that means our system is empty right now, and that means that we needed to go into that regenerative analysis. That's why it has the break statement right there. Secondly, we have if there's an arrival coming in and our L is, if there's an arrival coming in, our L is not equal to 0. So if an arrival comes in, that means we have one more out of the line, and because one person's arriving in the system, that means one more person's in line. And we have our time is right here. This is determining the partial length of the current cycle. And then if there is a departure coming, this means that you're in the departure state. This means that you're in the arrival state, sorry, the one above it. And the line decreases because somebody left the system, which makes sense. And then if we have the T equals infinity, but then we have this right here. Just basically, this is just a statement to check this statement above and to make sure that we have our time of departure. So we're adding the system time of departure. So basically, what we're doing is we're adding all the times of all the times of it adding up and all the times of it leaving, and we're storing that R and that T value from it. So we are trying to find the average length. So now we're going to be moving into the hospital ward problem. This is an emergency ward with a certain number of beds available for patients. Patients arrive based on Poisson distribution, and patient service time is based on a Weibull distribution. So basically what happens is you have a certain number of beds, and it's an emergency room, so people are coming in, and you need to make sure that that person gets a bed on time because they're in a state of emergency. So basically it goes through this process right here. If a patient arrives and all the beds are occupied, so that means every one of the beds is full and everybody's there, then if the patient is under a certain time, so if any of the patients in any of the beds are under a certain time, I think in the book they labeled it alpha, so if it's under like 1 minute left on their service time, they will be discharged early, which means they're an early departure, and the new patient takes that place. So basically what that means is if there's a certain person is under a certain amount of service time, a new person comes in, and if all the beds are full and none of the beds are underneath that service time, then the patient is referred to another hospital because they need to be served for their severe wounds. The goal of this is to find the utilization of all the beds in the system. So moving on. To the how the system works. This is also based on a three-phase method, just like the previous example. The first state is a arrival, so an arrival coming into the system. This is a bound state. A regular departure leaving the system. This is also a bound state. So these are things that happen and they're going to happen. And then there's the conditional state. So a conditional state basically means there's 3 different conditions that could happen, whereas above only one thing can happen. Whereas this one, possibly 3 things can be happening. So a patient is being served. Either they can have a normal admission, that means a bed is free. They can have an early departure, which means that one of the people who was in a bed needed to be discharged because they were under that tolerance limit. Or a referral. Referral means that all the beds are full, all the people are still being served over the threshold, so that person needs to be referred to another hospital. The simulation relies on the sort method. Basically what you do is you sort your bed's services times from smallest to largest. You take the smallest time and you only need to check the smallest time rather than checking all the service times. This decreases the complexity of the problem, makes it a lot quicker, it makes it a lot more efficient. And this smallest time is basically how you figure out the conditional states of this problem. So moving forward, this one will also have a regenerative analysis for whenever the state is empty, whenever the system has no arrival coming in at a certain point. And basically the aim of this is to find the utilization of the beds. So how many percent of the time are all the beds full in that system. So with that, that is it.